Hey folks, welcome back. So today we're going to be learning about how to actually compute determinants. Remember last lecture we learned some of the basic properties and we learned what determinants represent. They represent, the area, the sort of growth factor of a linear transformation. And today we're going to see how to actually compute it. So we're still on week 9's notes and we're just going down to page 6. All right, and we're going to start down here at computation. And before we get going into the computation, there's just one sort of technical note that I want to make you aware of because you might get an answer on an assignment or a midterm or something like that throws you for a bit of a loop, but it is okay. And that note that we've got to make is that the determinant of a matrix, it can actually be negative, even though we're thinking of the determinant as measuring an area or a volume, okay? And while this seems a little bit weird at first, you've actually seen something like this before in previous classes. So think back to calculus classes when you learned about something called the definite integral of a function, okay? So you had, here's a graph of a function, this is y equals f of x. And you talked about computing the area under the graph of this function. So you had something like, here's x equals a and x equals b. And you said the integral of that function was just the area under its graph above the x-axis between x equals a and x equals b. So this area right here was the integral from a to b of f of x dx. Okay, so you thought of the definite integral as representing an area, except definite integrals can also be negative sometimes. So you've also seen things like this, where if the graph of your function sometimes is positive but sometimes it's negative. All right, so again, here's y equals f of x, graph of a function. And then this time, here's x equals a. But now x equals b is over here. Then what the definite integral is actually computing is, well, this area above the x-axis under the graph of the function minus this area over here below the x-axis above the graph of the function, right? Remember, it's sort of a signed difference of positive areas minus negative areas, or areas below the x-axis. All right, oops. So in this case, you would have something like the integral from a to b of f of x dx equals, well, it's that positive area minus the negative area. Right? And something similar happens with determinants. We don't just think of determinants as measuring area, but actually they measure, here I'm going to scroll back to the first page, they measure signed area, okay? And what we mean by that is they don't just measure how much space is expanded, but they also keep a recording of whether or not the orientation of space was flipped, okay? So in the picture that I drew over here on the right, this matrix, it's not flipping the orientation of space, okay? And what I mean by that is you'll notice that, okay, on the input picture, E1 is clockwise from E2. On this output picture, A times E1, it's still clockwise from A times E2. All right, so here the determinant's going to be positive, and it really is just this output ratio, this output area divided by input area. Okay, so the determinant's going to be positive in this case. But if the matrix A was such that AE1 got sent to this left vector, and E2 got sent to this right vector, that would be a matrix with negative determinant, because now E1 got sent to something that's counterclockwise from where E2 got sent, okay? It sort of swapped the orientation of space. You can think of it as, that matrix, it not only sort of stretched and skewed things a bit, but it also reflected space if it reversed the orientation, okay? So in that case, the determinant would be negative. All right, so determinants can be negative is the short version of that, and there's nothing wrong with that, okay? It just keeps track of whether or not space was reflected as the matrix was applied. Okay, so let's see how we actually compute determinants, okay? If we're given just a general matrix, not diagonal or anything like that, how do we figure out what its determinant is? And the standard method, the quickest method for doing it, is just based on this Gaussian elimination procedure that we've done over and over and over before. So you use the same method that you use to solve linear systems of equations, okay? And each row operation that you do has sort of an easily predictable change that it applies to the determinant of the matrix. So if you're able to row reduce your matrix all the way way down to the identity, which we know has determinant 1, then you're done, because then you can just sort of trace back and see how much the determinant changed at each step as you got down to a matrix that has determinant 1. All right, so that's what this theorem here says. All right, so what it says is if you have a matrix and you're starting off with matrix A and you want to know its determinant. Well, what you do is you row reduce it to matrix B, and well, depending on which row operation you did, the determinant's going to change a different amount as you go from A to B. So if you did a multiplication row operation, what's going to happen is the determinant is just multiplied by whatever the scalar in that multiplication row operation is. All right? And, well, if you do an addition row operation, what happens? Actually, this one's a little surprising. The determinant doesn't change at all. If you do an addition row operation, no matter what that scalar C in the addition row operation is, the determinant doesn't change at all. You can do row 1 plus 23 row 2. Doesn't matter. The determinants of those two matrices are the exact same as each other. All right. And then the last one, this is sort of where negative determinants come from, actually. If you swap two rows of a matrix, the determinant, it just picks up an extra minus sign, all right? And again, this sort of corresponds to the fact that we talked about where sort of a negative determinant corresponds to space being reflected. And that's exactly what swapping two rows does. That sort of builds a reflection into that linear transformation. Okay. Anyway, so let's see how we actually make use of this theorem. The idea is you want to row reduce your matrix as much as possible. If you're able to get down to the identity matrix, then great. You know, identity matrix has determinant 1, and then you can just trace back the changes that you made to the determinant all the way back to your original matrix to figure out what its determinant must have been. On the other hand, if you row reduce and you're not able to get to the identity matrix, remember that means your matrix is not invertible, right? If the reduced row echelon form of your matrix is not the identity matrix, then your matrix is not invertible. And what that means is, well, we have a theorem from earlier in this week that says if your matrix is not invertible, that means the determinant is 0. Okay, if your matrix is not invertible, then your determinant is 0. So when you're row reducing, one of two things is going to happen. You're going to get identity and you can trace back to find the determinant, or you're going to get not identity and you know right away determinant must be 0. Okay, so let's see how to do this. Let's compute the determinant of this 3x3 matrix here. So let's just start row reducing. And it's very important when you do this to keep track of which row operations you're doing, because we're going to need them to compute the determinant at the end of the day, okay? Before, when we were solving linear systems, we just sort of kept track of them so we could keep track of the work that we did and, you know, make assignments and stuff easier to mark. But now we're actually going to need them to solve the problem. So keep track of your row operations. So here, I want to get zeros in these two entries below the leading entry at the top left. So I'm going to do row 2 minus row 1, and also row 3 minus row 1. Row 1's not going to change when I do those, so I just copy it down so I don't screw it up. I'm going to get 0 there. That's why I did that row operation. And then I get 1, then 3. I'm going to get 0 at the bottom left. That's why I did row 3 minus row 1. And I'm going to get 2 and 8. All right. Next up, I want to get rid of this 2 in the bottom middle. Okay, so I'm just going to do row 3 minus 2 row 2. And actually, because I want to go all the way to reduce row echelon form, I'm also going to get rid of this 1 above the next leading entry, right? Remember, the leading entry is this one in the middle here, this middle one. Because I'm going all the way to reduce row echelon form, I want to get zeros above and below it. All right, so I'm going to do row 1 minus row 2. That'll give me a 0 in the top middle. I'm going to do row 3 minus 2 row 2. That'll get me a 0 in the bottom middle. All right, copying down the second row, because that's not going to change. I don't want to screw it up. And then the top row, I'm still going to have a 1 there. That's not going to change. I get a 0 there. That's why I did row 1 minus row 2. I'm going to get a minus 2 up here. Bottom row, I'm still going to have a 0 there. I'm going to get 2 minus 2 in the middle, which is 0. That's why I did row 3 minus 2 row 2. And then I'm going to have 8 minus 6, which is 2 in the bottom right. All right, so I'm not too far away from reduced row echelon form now, just a couple more row operations. Next up, I have a leading entry in the top left, in the middle, and at the bottom right, but this leading entry at the bottom right, that 2 that I just circled, well, that's not a 1, right? I want to go all the way to reduce row echelon form because I want to see if I can get to the identity, because that's sort of the only matrix whose determinant I know. All right, so I'm going to do 1/2 row 3. I want that leading entry that's a 2 to be a 1. All right, so when I do this, the only thing that changes is that leading entry at the bottom right becomes a 1. All right. And now just one more pair of row operations to get all the way to reduced row echelon form. I'm going to do row 1 plus 2 row 3. That'll get me a 0 in the top right corner. All right, and then row 2 minus 3 row 3. And that'll get me a 0 in the middle right. And after I do this, I'm just going to be the identity matrix now. All right, there we go. So great. Okay, so we've gotten all the way down to the identity matrix now. What does that tell us, though, right? We row reduced it. We know the matrix is invertible because it's reduced row echelon form as the identity, but what does that tell us about the determinants? Well, just trace it backwards now. After you've row reduced to the identity, just say, okay, great, that's the identity. And I know the identity has determinant 1. Right? And now just go back one step at a time, asking yourself, how did the determinant change when I did that row operation? So if I go back one step, so in other words, if I think about what would happen if I undid this row operation here, well, then I would be back at this matrix. But all I did between these two matrices is I did addition row operations. And how do addition row operations change determinants? Well, that's answered by this theorem up here. Addition row operations, they don't change determinants. Okay, so if this matrix down here has determinant 1, and I only did addition row operations in between, then this matrix must also have determinant 1. Because addition row operations don't change determinants. Okay, and now just keep on doing this one step back at a time. Now if I go back one more step, in other words, I think about undoing this 1/2 row 3 and go back to here, well, how did the determinant change? Well, again, it's answered by your theorem. Multiplication row operations, they just multiply the determinant by whatever the scalar in the multiplication is, okay? So in this case, 1/2. All right, so be a little bit careful here. What this means is that going from this matrix over to this matrix, the determinant was multiplied by 1/2, going from left to right there. All right, so that means this matrix on the left must have determinant 2. Right? Because it's got to have determinant equal to something such that when I multiply it by 1/2, I get 1, right? The determinant on the right. All right, now you can just, I mean, it makes more sense now that we got it written down. If I start off with determinant 2, multiply it by 1/2, do I get determinant 1? Yeah, you do, okay? So just be careful. You're dividing by, because we're going backwards, right? We're dividing by 1/2 to turn 1 into 2. All right, now same thing, just keep going backwards. Addition row operation goes back to this guy. Well, again, addition row operations do not change determinants. So this matrix over here must also have determinant 2. Determinant equals 2. All right, and then finally go back one more step. Again, addition row operations get us back to here. So this must also have determinant 2. Again, addition row operations do not change the determinant. All right, so our conclusion at the end of the day, after we undo all those row operations, is that, hey, determinant of the matrix that we started with, well, it must have been 2. Okay. All right, so that's how it works. You go through Gaussian eliminations, but be really careful. Make sure you list every single row operation that you do to get to reduced row echelon form, because you need to then go backwards, trace your steps back through the through the Gaussian elimination, the Gauss-Jordan elimination actually, and just check for all of the multiplication row operations that you did, and also if you did any swaps, you have to keep track of them as well. Okay, so the addition row operations, they're free, but you have to be really careful about the other ones. All right, and so there's actually a slightly quicker and slightly easier way to do this procedure, okay? So we compute the determinant by going all the way to reduced row echelon form. Now we're gonna see that actually you can compute the determinant just by doing Gaussian elimination. In other words, just by going to row echelon form. You don't need to go all the way to reduced row echelon form. All right, so let's see how this works. And it's based on this theorem here. This theorem here tells us right away, it just gives us an explicit formula for the determinant of a triangular matrix. So remember, a triangular matrix, it's one that just has all zeros either below the diagonal or above the diagonal. So the only interesting stuff happens either in the top right or in the bottom left corner. Well, so what this theorem says is that if you have a triangular matrix, then its determinant, it's just the product of its diagonal entries, okay? So that's what we've got written here. The determinant of a triangular matrix just equals, well, the first diagonal entry times the second diagonal entry and so on, down to times the last diagonal entry. All right, so let's see where this theorem comes from. And basically it just comes from this procedure that we talked about up here. All right, so suppose that you've got some triangular matrix. All right, so I'm just going to write down a big ugly triangular matrix. All right, so A is, well, it's got A11 in its first diagonal entry, and then A22 in its next diagonal entry. And I'm going to assume that it's upper triangular. It doesn't really matter. The same sort of argument works if it's lower triangular as well. So I'm going to assume that all these entries in the bottom left are zeros, and then it's just got some entries in the top right. So they can be non-zero in the top right corner there, but I don't care about them enough to even give them names. It's just there's some junk up there. Okay, and I'm going to think about, well, how could I row reduce this down to the identity matrix, right? Because that's what I got to do to find its determinant. Okay, well, to row reduce this down to the identity matrix, one thing that I could do is, well, first off, I could scale all of those diagonal entries to be 1. Okay, so this assumes a little bit that the diagonal entries are non-zero. I'll talk about that in a second, though. For the most part, this is okay. So I could do 1 over A11 times row 1. And then I could do 1 over A22 times row 2, down to 1 over ANN times row n. All right, and what would our matrix look like after we do that? Well, now we're going to have a 1 in that top left entry, right? Because we just divided it by A11. We're going to have a 1 in the 22 entry because we divided it by A22, and so on down the line. All these diagonal entries now after we do this are going to be 1s. We're still going to have zeros in the bottom left corner. And in the top right corner, we're still just going to have some ugly crap. Okay, so it's a different ugly junk than we had before, right? This star is not necessarily the same as this star, right? Because we divided through these rows by, constants that aren't necessarily equal to 1, but it doesn't matter. There's still just some junk in that top right corner. All right, and now how could we get from here to the identity matrix? Well, just do a bunch of addition row operations, right? If you wanted to get a 0 in this entry just above the 1 over here, you would just do an addition row operation, right? You would do row n minus 1 minus some multiple of this row down here. But remember, all of these addition row operations are free. They don't change the determinant. So from here, you can just use addition row operations to get from here all the way to the identity matrix. So the n by n identity matrix. Maybe I'll put a subscript n there. All right, and now we can do the same thing that we did before. You just trace this backwards, keeping track of the row operations that you did to figure out the determinant of the original matrix. This matrix identity over on the right here, that has determinant 1. Well, that means this matrix here, because these two matrices on the right are related by addition row operations only, that means that this matrix must also have determinant 1. Right? Addition row operations are free, and then if we go back one more step, now these two matrices are related by these row operations. And again, remember, be careful, because we're going backwards, we divide by these scalars here. Okay, so to compute the determinant of this matrix on the left, we have to divide by 1 over A11. And we have to divide by 1 over A22, and so on. So in other words, what happens is, well, basically the division by a fraction just sort of undoes that fraction, right? The determinant, it's going to be 1 divided by A11. It's just going to be A11. And then times the next one. 1 divided by A22. Well, that's A22. And so on down the line, all the way to ANN. All right, and that's exactly what we wanted to show. We wanted to show that an upper triangular matrix has determinant equal to A11 times A22 times, and so on up to ANN. All right, so that's the idea behind the proof here. So I made a couple assumptions going through this proof, and the big one that we haven't dealt with is, well, what if one of these diagonal entries equals 0, right? Because then I can't do this row operation here. I can't do this multiplication operation to scale it to be 1 then. And so it turns out that if you have a triangular matrix and one of its diagonal entries is 0, then you know right away, actually, it's not invertible. If one of the diagonal entries of a triangular matrix is 0, then it's not invertible, which means that its determinant must be 0. Again, that was a theorem from earlier. So this formula still works even in that case, because if one of the diagonal entries is 0, so if one of these is 0, then, well, one of the entries in this product is 0, So you still get determinant being 0 from this formula too. All right, so it works out in either case. We assumed in this proof here that it was invertible, but it also works in the non-invertible case. All right. So the use of this theorem is that it lets us do this sort of procedure a little bit quicker. It lets us compute determinants without going all the way to reduced row echelon form. We only need to go to row echelon form now. So again, let's see how this works. Let's go through an example. This time a little bit larger. We're ramping up here, so 4x4 example now. Same basic procedure, just only row echelon form instead of reduced now. So I'm going to do row 2 minus row 1. And again, the reason for that is I want to get 0 here because I've had a leading entry at the top left corner. I want to get zeros below it. All right, so only row 2 is changing. Just going to copy down everything else before I do any actual math so I don't screw anything up. So copying down rows 1, 3, and 4. All right, and now row 2, I'll just subtract row 1 above it. Okay, and let's see, I get -1 there, -1, and still just 3 over here on the right. All right, great. All right, next up, I look for my next leading entry. Well, okay, here's my next leading entry in the 2, 2 spot, so I want to get zeros below it. If I was going to reduce row echelon form, I would probably also want to get a 0 above it, but I'm not going to worry about that. I'm also not going to worry about rescaling the leading entries to be 1s, because again, I'm only going to row echelon form, not reduce row echelon form. I can save myself that little bit of work. All right. If you want to rescale this leading entry so that it's 1, that's fine. You can do that, but I'm not going to do that. I'm just going to go straight to row 3 minus row 2. And row 4 minus row 2. 1, 2, 3, 0. And, sorry. 0, -1, -1, 3. All right, and now let's compute rows 3 and row 4. So 0, and then -1 minus -1. Be careful of your double negatives here. It's -1 plus 1, you get a 0 there. That's why we did that row 3 minus row 2 row operation. And then 1 plus 1, again, double negative here. We're going to have a 2 there, and 0 minus 3 is -3. And then row 4, 0, and again, double negative here gives us a -1 plus 1 is 0. Be careful there. 3 plus 1 is going to be 4, and then 0 minus 3 is -3. All right, and now we just have one row operation left to do because now, hey, here's our next leading entry in the 3, 3 entry. We want to get a 0 below it. All right, so now I'm going to do row 4 minus 2 row 3. Again, these aren't necessarily the row operations that you have to do. You could rescale this 2 to be a 1 if it makes you more comfortable, but it's going to introduce fractions that I just want to avoid, okay? There's sort of no need because 2 goes evenly into 4 anyway, so it's not too hard to do the row operation directly. All right, I'm not changing rows 1, 2, and 3, so I'm just going to copy them down so I don't screw them up. And the new row 4 is, well, 0 minus 0, 0 minus 0. 4 minus 4 is 0. That's why we did that particular row operation. And then -3 plus 6. Again, double negative. Be careful there. -3 plus 6 is +3. Great. That's far enough. Now we're in row echelon form. That's far enough to figure out the determinant, thanks to this previous theorem. All right? And the trick is, well, every row echelon form is upper triangular. Okay, here's a row echelon form, and yeah, it's upper triangular. Everything in the bottom left corner is 0. Okay, so we can use this previous theorem, the theorem just above. All right, so the determinant of this matrix at the end here, the determinant is 1 times -1 times 2 times 3. Right, I'm just multiplying the diagonal entries together, because that's what the theorem told me to do. So that's -6. All right, so this matrix at the end has determinant equal to -6. Well, now just trace it back, okay? Go back one step. Well, so I want to go back to here. What did I do in between those two matrices? I did an addition row operation. Addition row operations are free. They don't change the determinant. So this also has determinant equal to -6. Go back one more step. Go back to here. Well, how did I get from here over to the right? I did addition row operations. Again, addition row operations are free. They don't change the determinant. So this matrix also has determinant equal to -6. And finally, go back one more step. How did I get from A to this matrix? Well, I did an addition row operation. And again, those are free. They don't change the determinant. So the determinant of this original matrix that I started off with, that must have also been -6. All right, so we're just done. Our conclusion is that the determinant of that matrix that we started with, it's -6. Okay, we would have to be a little bit more careful there if we did do any swaps or any multiplication row operations. Just be careful to undo those determinant changes as you go backwards. So either divide by the scalar in the multiplication or multiply by -1 if you do a swap. But we only did addition row operations, which are easy. Okay. All right, so that's sort of the standard way of computing the determinant. That's the quickest way. All right, but now what we're going to look at is there's actually a slightly different way that you can use to calculate determinants as well. There's some explicit formulas for determinants that you can use, at least for small matrices, for like 2x2 and 3x3 matrices. Okay, these methods aren't quite as quick, at least once you get to larger matrices, but it's still nice because, I mean, explicit formulas are nice, right? All right, so let's have a look at these. So starting off with sort of the easiest case, the case of 2x2 matrices, well, it turns out that there's an explicit formula for the determinant of a 2x2 matrix. You don't have to go through Gaussian elimination at all. It's just you plug into this formula and you're done. Okay, so here's how it works. Suppose that you've got a 2x2 matrix and we just give names to its entries, call them A, B, C, and D. It doesn't matter what you call them, but that's what we chose. The determinant, it's AD minus BC, and that's it. Okay, it's really that easy. So what we're doing here, the way to think about this formula, the way to remember it, is what we're doing is you just take the entries on the main diagonal, you multiply those together, right? That gives you this AD piece. And then you take the entries on the backward diagonal, the entries going back this way, B times C, and you subtract that product off. So you think of it as forward diagonal minus backward diagonal. That's what this formula is. All right. And we're going to see where this theorem comes from, okay? We're going to prove this by going right back to sort of the defining properties of the determinant. And in particular, we're going to make use of multilinearity. That was defining property C of the determinants, okay? So just to remind you what this property was, you know, this was the one that said that the determinant is linear in the columns of a matrix. So it said that if you have any matrix where you do some sort of weird linear combination in one of the columns only, so something like this, so then you can, so I have a linear combination just in the first column there. Remember, it's not a linear combination of like the entire matrix. It's only one column at a time. Then what you can do is you can split that up over that column, leaving every other column alone. Okay, so that second column, which is X, that's just got to stick around. Oops, I want X to be blue. All right, so it's going to be the determinant of the matrix that just has V in the first column, and then plus C times the determinant of the matrix that just has W in that first column. Okay, so remember that's you know, that's sort of the 2x2 version of that multilinearity property from back in the definition of the determinant. Right? And we're going to make use of that here to prove this theorem. So here's how it goes. We want to compute determinant of A, B, C, D. So I'm going to start off with that. All right, but now I'm going to use multilinearity. I'm going to split up that first column in a clever way, okay, leaving the second column alone. Remember, the second column is not going to change at all when I do this. All right, so here's how it's going to look. All right, so I left the second column alone, but I'm sort of I'm splitting up that first column as a linear combination of two column vectors. All right, so that's a true statement, and the reason for that is just because, well, the two first columns on the right, did those add up to the first column on the left? Well, yeah, right? It's just a linear combination. It's just, yeah, this plus this equals this. So that's how the determinant splits up, right? You can take that linear combination outside of the determinant, and all other columns in the matrix you just leave alone. That's just a BD everywhere. Again, remember the determinant is multilinear, not linear. So this works since that first column AC, well, that's A0 plus 0C. All right, so yeah, you can split up the determinant like that. All right, but the reason that we did that, the reason that's a clever thing to do, is now look at these two determinants over on the right. In particular, let's focus on the first one. This is upper triangular, right? It only has 0 stuff in the bottom left corner. So this is upper triangular. We know from our previous theorem that the determinant of an upper triangular matrix, it's just the product of those diagonal entries. So this first determinant, we know it right away. It's A times D. It's the product of those two diagonal entries. All right. The second determinant, the determinant of this weird 0BCD matrix, that's a little bit harder because that's not upper triangular or lower triangular. Upper triangular and lower triangular, they're in reference to the main diagonal. They talk about only being zeros on one side or the other of this diagonal. The fact that there's a 0 at this top left corner, that doesn't tell us anything about upper triangularity or lower triangularity. We don't have any nice theorems about these types of matrices. But that's actually not as much of a hindrance as you might think, because we can do one single row operation to turn this matrix into an upper triangular one. In particular, what I'm going to do is I'm just going to swap the 2 rows of that matrix. Oops. Sorry. And the thing that I'm going to have to be a little bit careful of is, remember, when you swap 2 rows of a matrix, the determinant gets multiplied by -1. All right, so to get from here to here, I swapped 2 rows of the matrix. And what that does is it multiplies the determinant by -1. So this plus between the two determinants, it's got to switch to a minus, okay? Because that determinant, now it's got an extra minus sign in front of it. All right, and now this basically immediately gives us what we want. We still have that AD in front. But now, hey, determinant of this matrix, again, that's upper triangular. Where its diagonal entries, B and C, just multiply them together. That gives you your determinant, because the determinant of a triangular matrix, it's just the product of the diagonal entries. So that's where this formula comes from. It's AD, because you can split it up into one matrix that has AD on the diagonal, minus BC, because you can split it up into another matrix that has B and C on the diagonal. And then we're done. All right, great. All right, and yeah, the way to remember this theorem is, it's forward diagonal minus backward diagonal, AD minus BC. All right, so let's actually use this. Let's see an example of how to use this formula here. So let's compute the determinant of this matrix, 1, 2, 3, 4. All right, well, just plug into the formula. Determinant of A is the product of the things on the forward diagonal, well, 1 and 4, so it's 1 times 4, minus the product of the things on the backward diagonal, 2 times 3. So that's 4 minus 6. And that's -2. Great. All right, so that's our determinant. And, well, let's just sort of check our work. Let's compare it with another method. Let's call that method 1. Actually, let's call that method 2, because it's the second method that we learned. So that's method 2 of computing the determinant. Nope, that's not how you spell method. Method 2. All right, let's try another method. So let's go through method 1, which was, Gaussian elimination. Let's row reduce this matrix to find its determinant. All right, well, if we were row reducing this, then we would do row 2 minus 3 row 1. That would leave row 1 alone, so it's still 1, 2. And row 2 would now be 0, and then 4 minus 6 would be -2. So there we go. All right, and now we would look at this and we say, okay, well, what's its determinant? Well, the determinant of this matrix, this row echelon form that I just computed, that's upper triangular, so its determinant is just the product of the entries on its diagonal. So this matrix over on the right here, this row echelon form, that has determinant -2. And because we just did an addition row operation, and addition row operations are free, this matrix must also have determinant -2. All right, so over here, we also conclude, yeah, great. Determinant of A is -2. All right, so it's a very different method, but of course you get the same answer either way, okay? We would hope that our explicit formula would agree with our method based on Gaussian elimination, and it does. So you can use whichever method you like, okay? It's entirely up to personal preference. If you can remember the formula, great. makes it fairly quick and easy. But if you can't, this method based on Gaussian elimination, it has the advantage of being very quick for larger matrices, and it does work no matter what the size of the matrix is. This formula only works, this explicit formula that we just went through only works for 2x2 matrices. All right. Well, it turns out that there are explicit formulas for larger matrices, though. So let's go through the 3x3 case. All right. So here, there's an explicit formula for 3x3 matrices. And here it is. So suppose you got some 3x3 matrix. Just give names to its entries: A, B, C, D, E, F, G, H, I. It doesn't matter what you call them, but just give names. It turns out that the determinant of any 3x3 matrix is this big, hideous, ugly mess. Okay, so all of a sudden, explicit formulas are getting a little bit harder to work with, but there is actually a nice mnemonic that you can use for this particular case, for the 3x3 case. And it's sort of, again, it's based on sort of forward diagonals and backward diagonals. So let's go through how this works. All right, so how can you actually remember this big, hideous, ugly, long formula here if you want to know an explicit formula for 3x3 matrix determinants? Well, what you do is, sort of the succinct way to state this determinant formula here is it's the sum of the 3 forward diagonals minus the sum of the 3 backward diagonals. So what do we mean by that? Well, what I'm going to do here is I'm going to write down this matrix again. So A, B, C, D, E, F, G, H, I. All right. And now I want to talk about 3 forward and 3 backward diagonals of this matrix, except I have to be a little bit careful when I do this because, I mean, yeah, okay, there's this forward diagonal right here. Great. But if I try to do forward diagonals starting anywhere else in the matrix, you know, I sort of get stuck partway down. So I want to think about this matrix as looping around, okay? So what I'm going to do is I'm just going to write additional copies of this matrix beside itself. All right, so I'm going to write A, B, C, D, E, F, G, H, I on its right and on its left. Okay, so just another copy of the matrix on its left and right, just to make it sort of easier to picture what's going on here, because I'm going to talk about these diagonals looping around. All right, so what you do, the way this formula works, is you take the forward and backward diagonals starting at each of the different top entries in the matrix. Okay, so I've already drawn on here one of the diagonals, so the forward diagonal starting at A. All right, and if you just multiply together the 3 entries on that forward diagonal, you get A, E, I. And actually, sorry, I'm going to do that term in green. You get A, E, I. All right, now we'll just do another forward diagonal, but starting at the next entry in the matrix. Okay, so starting at B. And if I do that, I get B, F, G. All right, so that's the next term in my determinant, BFG, okay? And sort of what I mean by these diagonals looping around is here, you know, I did BFG and it sort of goes on over to the right outside the matrix. You could also think of that, though, as like BF, and then like it sort of wraps around in the matrix and goes down over there and goes through that G, okay? So that's sort of what I mean when I'm saying that I think about these diagonals as looping around the matrix. All right, and then you have one more forward diagonal that you can do. You can do C, D, H, or alternatively, you can think of that as going through C and then it loops around to the left side of the matrix and goes through DH. Either way, the next term in the determinant is CDH. All right, so you have 3 forward diagonals. Those give you the 3 positive terms in that determinant expansion. You also have 3 backward diagonals, so you can do this exact same thing. Start at the same 3 entries in the top of the matrix, A, B, and C, but just have the diagonals go back the other way, and those will give you the negative terms in the determinant. All right, so A, F, H minus A, F, H. Okay, B, D, I minus B, D, I. C, E, G. Okay, so minus C, E, G. All right, so the 3 forward diagonals get plus signs, the 3 backward diagonals give you minus signs, okay? And that, if you go back and compare really carefully with that formula on the previous page, that is the exact same formula, AEI plus BFG plus CDH minus AFH minus BDI minus CEG. No one actually remembers that as sort of an explicit formula. They just remember the mnemonic for computing it. Okay, forward diagonals minus backward diagonals. So let's see how this works with a sort of numerical example. Let's compute the determinant of a 3x3 matrix without doing Gaussian elimination. All right. So the determinants of this matrix, and actually maybe before we do this, I should mention we didn't actually prove this theorem. It turns out that proving it, it's almost the exact same as proving the formula for the 2x2 case. It's just ramped up. It's just you have to use multilinearity multiple times rather than just one time, like we did in the proof for the 2x2 case. All right. Anyway, without that out of the way, let's compute the determinant of this matrix. So we have 3 forward diagonals. All right, the first one is, oh, come on. All right, so the first one is 1, 2, 9. So we're just going to multiply 1 and 2 and 9. That's our first forward diagonal. Next forward diagonal is 1, 4, and then loops around a 1. Okay, 1, 4, 1. And the next one is 1 loops around to 1, 3. Okay. So those are the 3 positive terms, and then minus our 3 backward diagonals. So let's do those next. 1 loops around to 4, 3. 1 times 4 times 3. And then minus 1, 1 loops around to 9. And then finally, 1, 2, 1 is our last backward diagonal. And now we just compute all these products and add them up. So that first one, that's going to be 1 times 2 times 9 is 18. Next one is 4. Next one is 3. And then minus 1 times 4 times 3 is 12. And then minus 9 and minus 2. And then you just add all this junk up. So let's see, 18 plus 4 plus 3, that's going to be 25. Minus 12 brings us down to 13. Minus 9 brings us down to 4. Minus 2 brings us down to 2. All right, so the determinants of this matrix is 2. And again, maybe just as a sanity check, let's go back. We already computed the determinants of this matrix earlier this class, actually. All right, so let's just scroll back up a couple pages. We computed this determinant via the method based on Gaussian elimination. This is exactly this matrix whose determinant we computed earlier. And of course, we got the exact same answer. We got determinant of 2 was back then as well, okay? So yeah, I mean, these explicit formulas, of course, they give you the exact same thing as if you... as if you use the Gaussian elimination method. All right, so... All right, now these explicit formulas, it turns out that they can be generalized to 4x4 matrices and 5x5 matrices and so on. We're not going to go through that. Again, just because we're sort of in triage mode here, we're only going through the things we absolutely have to go through. We're not going to go through what's called cofactor expansions. These are the ways of generalizing, this is the way of generalizing 2x2 formula and 3x3 formula to larger matrices. We're not going to go through it, okay? So if you want to compute the determinant of a 4x4 or larger matrix, use the method based on Gaussian elimination or Gauss-Jordan elimination, you know, row reduced to a row echelon form or reduced row echelon form. So you'll not be tested on this, okay? I left it in just because I want you to be aware that it exists, okay? You might see at least mention of it later on in some math course or something like that, or in some physics course. So I want you to be aware that it exists. We're not going to go through actually using it though, okay? So it's just another way of computing the determinant of large matrices. All right, and you can sort of wrangle around with cofactor expansions to actually get explicit formulas for any size of matrix that you like, okay? So for 2x2, the explicit formula, again, it's AD minus BC. For 3x3s, the explicit formula is this thing here. I mean, it has 6 terms. Each term is the product of 3 entries in the matrix. If you use cofactor expansions and go through this method that we're skipping over, you can come up with an explicit formula for the determinant of a 4x4 matrix. And it turns out you get exactly this formula here. This is an explicit formula for the determinant of a 4x4 matrix, but this sort of hopefully illustrates why we don't use explicit formulas for 4x4 and larger matrices. I mean, this formula here, it's an absolute nightmare. There are 24 terms in this formula here, and each of those terms is the product of 4 entries from that matrix A. Okay. In general, what happens every time you increase the size of a matrix by 1, say if you increase the size from 3 to 4, well, you multiply the number of terms in the explicit formula by the size of the matrix. So going from 2, like the 2x2 formula had 2 terms, the 3x3 formula had 2 times 3, which is 6 terms. To go from 3 to 4, well, the 3x3 formula had 6 terms, So to go up to 4, you multiply that by 4. Now you have 24 terms. 6 times 4 is 24. In general, you're going to get n factorial terms in the explicit formula for the determinant. So this grows ridiculously quickly, which again, that's why we don't use these explicit formulas for larger matrices. We use Gaussian elimination. For 5 by 5 matrices, there's going to be 120 terms in the formula for the determinant. And each one of those terms will be the product of 5 of the entries from the matrix. No thank you. Okay, so use Gaussian elimination if you ever have to find a determinant of a 4 by 4 or larger matrix. All right, so that's it for today. I will talk to you all again shortly when we start going through week 10's notes. All right, have a good one.